We're back with the first and second laws. Remember that this equation is for the total force acting. In memory of Galileo, here's a ball on a surface. It has weight, which is a vector, which I'll call W, and its direction is down. To hold it up requires an upwards force, which I'll call the normal force N, being supplied by the bench. I call it the normal force because it's at right angles to the bench, in the normal direction to the bench. I could also supply this force with my hand, and then I can feel that there's a force. The normal force is 1 of a Newton pair, and I feel minus N, the force that the ball exerts on my hand or on the bench. Now, when I place the ball on the bench, it turns out the normal force has a magnitude almost exactly equal to its weight. Their directions are opposite, so W plus N equals 0. Why they're almost exactly equal is a bit subtle, and you might like to reflect on that before we discuss it next week. This is one example of the situation we call mechanical equilibrium. Total force is 0, so acceleration is 0. When the ball is rolling with constant velocity, the horizontal force is also 0, so that's also mechanical equilibrium. The diagram I've drawn here, a vector representation of all the external forces acting on an object, is called a Freebody Diagram. Let's look at the slider. Here, the upwards force is the lift, L, provided by the compressed air underneath. It's in mechanical equilibrium at rest. At constant velocity, it's also in mechanical equilibrium. But at the ends, there are large horizontal forces and large accelerations. To solve problems in physics, there are several steps, and one of the most important is making appropriate approximations. Often it's the most difficult part of solving a problem. This is a simple example, but let's be careful and concentrate. Suppose I accelerate this trolley, mass 1 kilogram, by pulling on the string, mass 2 grams. What forces are required to give an acceleration of 2 meters per second per second? First, we can see that it doesn't accelerate upwards or downwards, so, by Newton's second law, the vertical forces add up to 0. Well, that's not very interesting. What horizontal forces are involved? Well, we can identify 2 Newton pairs. On your left side, the string pulls the trolley to the right, and the trolley pulls the string towards the left. They are a Newton pair, so they have the same magnitude. Call it F left. And on the right, my hand pulls the string to the right, but the string pulls my hand left. These have the same magnitude. Call it F right. Let's label these using Newton's third law. Now, the only external force acting on the trolley is F left. So we write F left is equal to MA is equal to 1.0 kilograms times 2.0 meters per second equals 2.0 newtons. What about the string? It's also accelerating at A, but 2 forces act on it. F left pulls it to the left, and F right pulls it to the right. So, Newton's second law allows us to calculate the difference between the forces at the left and right end. Because the string is light, this is only 0.004 newtons. So, F left equals F right to a very good approximation. And I'll call both of these forces the tension in the string. Now, the key to making this approximation is that the string is light. Its mass is much smaller than that of the other object. In physics problems, we often meet light strings. We wouldn't make that approximation if, instead of using a string, I used a chain. Strings and chains are also often described as inextensible, meaning that they don't stretch. If I used a rubber band, I couldn't even assume that the acceleration at both ends was the same. So, If the string is light and inextensible, our problem is simple. The force I apply with my hand equals the tension in the string, and the tension in the string accelerates the trolley and the string. But because the string is light, I can write tension equals mass plus mass of string times A is approximately equal to mass times A. A further lesson. When I wrote tension equals mass plus mass of string times A, what happened to the other three force vectors? Let's see that next. There's another important thing about applying Newton's laws, and it concerns internal forces, the forces that one part of a body or system exerts on the other. As we saw before, these add to zero by Newton's third law. So, when we write Newton's second law, we only need to sum the forces external to the object or to the system that we're considering. Sounds easy? Well, let's see how you go here. The man says to the horse, "Get up," with horse language for go. The horse replies, "There's no point. Newton's third law says that the cart will exert a force on me equal and opposite to the force I exert on it. Sum of forces equals zero, so the acceleration will be zero." Okay, how would you answer the horse? Get out your secret weapons and draw a sketch before you answer.